In the third example, we shall examine the case where we need to know if there are enough characterized resources of one kind to match any of the characterized resources of another kind. As an example, consider the situation where we have flatbeds waiting to load SteelShapes. For SteelShapes to be loaded in a flatbed, their length must not exceed the length of the flatbed, and the total SteelShapes loaded must be at least 75% of the payload of the flatbed. In this case, we are interested to find the first flatbed in a FIFO queue that can be loaded. The first statement defines the filter SS that fit, which stands for SteelShapes that fit, which applies to resources of type SteelShape and whose logical expression is simply the number 1. This logical expression is simply a placeholder and will be redefined below. We need to define the filter SS that fit first because its name is required to define the filter FB can loaded, which follows. Filter FB can loaded stands for flatbed can be loaded and applies to resources of type flatbed. A flatbed passes this filter if the sum of the weights of the SteelShapes that fit in SteelShapes weight is greater than or equal to 75% of the payload of that flatbed. To evaluate this expression, we must first construct the subset that is formed by applying the filter SS that fit to the Q SteelShapes weight. That will give us all the SteelShapes whose length allows them to fit on the current flatbed. Once we have that subset, we then take the sum of the weights of those SteelShapes and we check to see if it is greater than 75% of the payload of the flatbed. If that is true, then the flatbed will be allowed to pass the filter FB can be loaded. In simple terms, the filter FB can be loaded singles out those flatbeds that have plenty of shapes and can be loaded. The next statement is new. This statement is filter exp, which stands for filter expression. This statement allows us to redefine the logical expression for a filter. In this case, we wish to redefine the logical expression for the filter SS that fit that was defined earlier. This logical expression means that a SteelShape passes the filter if its length is less than or equal to the length of the flatbed which is pointed to by the filter FB can be loaded. Notice that we have a circular reference here. The filter FB can be loaded uses the filter SS that fit, and the filter SS that fit uses the filter FB can be loaded. However, the filter expression for SS that fit does not reevaluate the subset formed by the filter because the filter itself is not applied to a queue. The expression FB can be loaded.length simply tells Stroboscope to return the length of the flatbed which is currently pointed to by the active filter FB can be loaded. The length on the left-hand side of the inequality is the length of the SteelShape that is currently pointed to by the filter SS that fit to see if it fits the flatbed pointed to by the filter FB can be loaded. That flatbed is inside the flatbed's weight queue. Notice that the filter SS that fit is subordinate to the filter FB can be loaded. This means that while the filter FB can be loaded is filtering the queue flatbed's weight, we will activate the filter SS that fit and filter the queue SteelShape's weight for that particular flatbed pointed to by FB can be loaded. These filter statements are used by the enough statement for link FB1, whose logical expression is simply the count of the subset formed by the filter FB can be loaded when applied to the Q FlatBed's weight. Remember that applying the filter FB can be loaded to the Q FlatBed's weight creates a subset, in this case, the subset of those flatbeds that can be loaded, and the dot count at the end simply tells us how many elements are in this subset. If that number is 1 or more, that implies a logical true. So the enough attribute for link FB1 would be true, and that would allow LoadShapes to create an instance. For a new instance of LoadShapes to draw the appropriate flatbed from the Q FlatBed's weight, we need a new filter. This filter is called SS.FitToDraw. It applies to resources of type SteelShape and allows only those SteelShapes whose length is less than or equal to the length of the flatbed pointed to by the link FB1. Notice that the logical expression for the filter SS.Fit and the filter SS.FitToDraw are very similar. The left-hand side of their logical expression is simply length. The right-hand side is the length of a flatbed pointed to by something. In the first case, for SS.Fit, the flatbed is pointed to by the filter FB can be loaded. In the second case, the flatbed is pointed to by the link FB1. The DrawWhere logical expression for link FB1 allows only those flatbeds that can be loaded to be drawn. This is determined as follows. Link FB1 points to a flatbed and then creates a subset of all the SteelShapes that fit to draw in the SteelShapes weight. In other words, it finds all the SteelShapes whose length is less than or equal to the length of the flatbed. Once it forms that subset of SteelShapes, then it adds their weights and compares that to make sure it is greater than or equal to 75% of the payload that link FB1 is currently cursoring. If that inequality is true, then the DrawWhere attribute for link FB1 is true, and link FB1 will draw the currently cursored flatbed. Otherwise, link FB1 will cursor the next flatbed in line and repeat the process to see if it can draw that flatbed. Because the enough attribute of link FB1 returned the value true, we know that there is at least one flatbed that can be loaded. So the DrawWhere for link FB1 will eventually be satisfied and a flatbed will be drawn. After the new instance of Combi LoadShapes receives a flatbed, it is time to draw the appropriate SteelShapes. This is accomplished through the DrawWhere attribute for link SS1. The logical expression of the DrawWhere for link SS1 is a logical end statement with a left side and a right side. The left side compares the length of the currently cursored SteelShape to the length of the flatbed currently in the instance of LoadShapes. In other words, the SteelShape must fit in the flatbed in LoadShapes. The second part of the logical end statement is that the weight of the currently cursored SteelShape must be less than or equal to the remaining capacity of the flatbed in LoadShapes. That remaining capacity is the payload of the flatbed in LoadShapes minus the sum of the weights of the SteelShapes already in the starting instance of LoadShapes. Link SS1 will cursor all SteelShapes one after the other and see if they can be drawn based on its logical expression. This will continue until the draw until for link SS1 is satisfied. The draw until for link SS1 is satisfied when the sum of the weights of the SteelShapes in LoadShapes is greater than or equal to the payload of the flatbed in LoadShapes. In other words, it is satisfied when the flatbed is fully loaded to its capacity. This can only happen by coincidence when the sum of the weights of the SteelShapes equals exactly the payload of the flatbed in LoadShapes. In most cases, it will not be satisfied, so the link SS1 will continue checking all the SteelShapes in queue until it gets to its very end. The interaction between the two filters FB can be loaded and SS that fit is explained using the two figures on this page. When the filter FB can be loaded is applied to the queue flatbed's weight, it cursors the first resource in line, which has resnum equal to 1, payload 8, and length 22. The filter FB can be loaded, then checks to see if this flatbed satisfies the logical expression of the filter. The logical expression of the filter examines the sum of the weights of the SteelShapes that fit in SteelShapes weight. That requires the application of the filter SS that fit to the Q SteelShapes weight. This is done in the second table. The application of the filter SS that fit to the Q SteelShapes weight begins by the filter SS that fit cursoring the first SteelShape in Q, which has resnum 1, weight 1.5, and length 18. The filter then evaluates its logical expression to see if this SteelShape passes the filter. The logical expression compares the length of the currently cursored SteelShape, which is 18, against the length of the flatbed currently cursored by the filter FB can be loaded, which is 22. In this case, the first resource passes because its length is 18, which is less than or equal to 22. The filter SS that fit will then cursor the next SteelShape and repeat the process. Is its length, which is 22, less than or equal to the length of the flatbed pointed to by the filter FB can be loaded, which is 22. This is true, so the second SteelShape also passes the filter SS that fit. The third SteelShape does not pass the filter because its length 24 is greater than the length of the flatbed currently cursored by the filter FB can be loaded, whereas the fourth SteelShape passes because its length 22 is less than or equal to 22. As a result, the subset formed of SteelShapes that fit includes three elements: resnum 1, resnum 2, and resnum 4. The logical expression for the filter FB can be loaded requires the sum of the weights of the SteelShapes that fit in SteelShapes weight. As a result, it wants the sum of 1.5 plus 2 plus 4, and then compares that to 0.75 times the payload of the currently cursored flatbed, which is 8. This requirement is true, which means that the first flatbed can indeed be loaded, so it passes the filter FB can be loaded and becomes part of its subset. The filter FB can be loaded then cursors the next flatbed in Q, which is the one with resnum 2. The exact same process is then repeated, and the filter SS that fit creates a subset of SteelShapes weight that includes all the SteelShapes whose length is less than or equal to 24. That includes all 4 SteelShapes. The sum of the weights of all these 4 SteelShapes is greater than or equal to 75% of the payload of the currently cursored flatbed, which is 9, so the second flatbed can also be loaded, and it also passes into the subset created by FB can be loaded. The filter FB can be loaded then cursors the third flatbed with length 20. It then applies the filter SS that fit to the Q SteelShapes weight to see what is the subset of SteelShapes that fit into this flatbed. In other words, what is the subset of SteelShapes whose length is less than or equal to 20. In this case, there is only one whose weight is 1.5. Because 1.5 is not greater than 75% of the payload of the flatbed, which is 6, then this flatbed cannot be loaded, so it does not pass the requirements of the filter FB can be loaded. The filter FB can be loaded then cursors the last flatbed in the queue, which has a length of 24. The results are exactly the same as for the second flatbed in queue, which means that this flatbed can be loaded too. So the end result of applying the filter FB can be loaded to the queue flatbed's weight is to create a subset that contains the flatbeds with rest numbers 1, 2, and 4. The logical expression for the enough attribute of link FB1 simply considers the count of the elements in this subset, which is 3. Because the enough attribute of link FB1 is true, activity LoadShapes will be able to create an instance. Notice that the enough attribute of link SS1 does not need to be evaluated because it is automatically true by evaluating the enough attribute of link FB1. As a result, the default enough expression for link SS1 is sufficient. When Combi LoadShapes creates a new instance, it will first draw a flatbed through link FB1. The evaluation of the logical expression for DrawWhere for the link FB1 is almost identical to the process of evaluating the enough expression for link FB1. The difference is that the filter to be applied is not FB can be loaded, but it is the DrawWhere filter of link FB1. The subordinate filter for the DrawWhere of link FB1 is not SS that fit, but the filter SS that fit to draw, which is very similar. So the process by which link FB1 identifies the first flatbed that can be loaded is very similar to the process by which link FB1 evaluates its enough attribute. We shall again consider the question whether there are enough characterized resources of one kind to match any of the characterized resources of another kind so as to allow an activity to start. The previous approach in 3.1 used two different filters, one for the enough statement and one for the DrawWhere statement. In this model, we will use a single filter. We will use the same filter for both enough and for DrawWhere. Just like in the previous model, we begin by defining the filter SS that fit that applies to resources of type SteelShape with a dummy logical expression that has just the number 1. The number 1 is a placeholder that will be replaced below. We then define a var prop for characterized resources of type FlatBed, which we shall call plenty shapes available. The logical expression for this var prop has two parts. The left part is the sum of the weights of the SteelShapes that fit in SteelShapes weight. On the right side, we have 75% times the payload of this flatbed. We then define the filter FB can be loaded, which applies to resources of type flatbed with the expression plenty shapes available. This expression is a var prop which will be evaluated for the flatbed that is currently cursored by the filter FB can be loaded. A flatbed can be cursored by either the FB can be loaded filter in an enough statement or the FB1 link in a DrawWhere statement. We define a variable that provides common access to the length of the currently cursored flatbed. This variable is called currently cursored flatbed length. Its expression is an if statement. The conditional part considers whether FB can be loaded has cursor. If that is true, then the expression returns the length of the flatbed pointed to by the filter FB can be loaded. If the filter FB can be loaded does not have a cursor, then it is not active, in which case we return the length of the flatbed pointed to by the link FB1. The next expression redefines the logical expression for the filter SS that fit. The expression for SS that fit compares the length of the SteelShape that is currently pointed to by the filter SS that fit to the currently cursored flatbed length. The currently cursored flatbed length is a conditional statement that returns either the length of the flatbed which is pointed to by FB can be loaded, or the length of the flatbed pointed to by the link FB1, depending on which of the two is currently cursoring the flatbed, FB can be loaded or FB1. It is this conditional statement in the variable currently cursored flatbed length that allows us to use a single filter SS that fit and not need the filter SS that fit to draw. The filter statements up to this point are not active until they are used by the enough statement for link FB1. The expression for the enough statement is simply the count of FB can be loaded in flatbed's weight. This expression simply returns how many flatbeds in the queue flatbed's weight can actually be loaded. If that number is 1 or more, then the logical meaning of that number is true, in which case the enough for link FB1 is true and it will allow the subsequent activity LoadShapes to start. If all the links entering the Combi LoadShapes return an enough that is true, then LoadShapes will be able to create an instance and it will have to draw resources through link FB1. The DrawWhere for link FB1 is simply the expression plenty shapes available, which is a varprop of the characterized type flatbed. This means that the link FB1 will point to the first flatbed in the queue flatbed's weight and evaluate its varprop plenty shapes available. The expression for the varprop plenty shapes available creates a subset of all the SteelShapes in the queue SteelShapes weight whose length is less than or equal to the length of the flatbed pointed to by the link FB1, and then sums up their weight. It compares the sum of the weight of the SteelShapes that fit into the currently cursored flatbed to see if it is greater than 75% of the payload of the flatbed that is currently cursored. If it is, then link FB1 will draw that flatbed. At this point, the new instance of LoadShapes will contain a flatbed that, according to the enough statement, should have enough SteelShapes available for it to be loaded. The next task is to draw those SteelShapes that actually fit in the flatbed inside the new instance of activity LoadShapes and whose total weight is between 75% and 100% of the payload of this flatbed. This is accomplished with the DrawWhere statement for link SS1, whose expression is a logical expression with two parts. These two parts are combined with a logical AND statement. On the left, we have a comparison of the length of the SteelShape currently pointed to by link SS1 to the length of the flatbed that has already been drawn and it is inside the new instance of activity LoadShapes. If the length of the SteelShape is less than the length of the flatbed, then that SteelShape could possibly be drawn. But there is another condition. On the right-hand side, we have to examine if the weight of this SteelShape is less than or equal to the available capacity on the flatbed. The available capacity on the flatbed is the payload of the flatbed currently in LoadShapes minus the sum of the weights of the SteelShapes that have already been drawn and are inside the instance of LoadShapes. If both sides of this logical end statement are satisfied, then this SteelShape will be drawn and be transferred into the new instance of LoadShapes. Otherwise, the link SS1 will bypass this SteelShape and go to the next one in line and repeat the process. The drawing process continues until the draw until for SS1 has an expression that returns true. The expression for the draw until for SS1 is a logical expression that compares on the left-hand side the sum of the weights of the SteelShapes in LoadShapes, in other words, the sum of the weights of all SteelShapes that have already been drawn, to see if they are greater than or equal to the payload of the FlatBed inside the instance of LoadShapes. Just like in the previous model, this logical expression cannot be satisfied as an inequality. It can only be satisfied as a quality in the case where there is a coincidence and the payload of the FlatBed in LoadShapes equals exactly the sum of the weights of the SteelShapes in LoadShapes. Otherwise, the FlatBed will not be loaded to capacity. Nevertheless, the link SS1 will continue attempting to draw and examine all the SteelShapes in the queue SteelShapes weight until it reaches the end of the queue. The pseudocode that follows illustrates the process that Stroboscope goes through when it evaluates the enough attribute for link FB1. This pseudocode is essentially two loops, one inside the other. The outer loop loops over the available FlatBeds, and for each FlatBed, the inner loop loops over all the SteelShapes to see if the weight of all the SteelShapes that fit inside the FlatBed have a weight that is between 75% and 100% of the FlatBed's payload. If that is so, then the FlatBed is added to the subset of FlatBeds that can be loaded. The key variable in this pseudocode is num of FlatBeds that can be loaded, which starts at 0 and is then incremented as needed through the two loops. If the final value is greater than 0, then the enough attribute for link FB1 is true. Note that loading SteelShapes onto FlatBeds can also be approached as an optimization problem, that is, like a knapsack problem. One such problem is to select the optimal set of SteelShapes to load onto the next FlatBed in the case where there are plenty of shapes available, or to dynamically allocate all currently available SteelShapes to all currently available FlatBeds in some overall optimal manner and to select which is the best FlatBed to load next. Clearly, such advanced optimization problems are well beyond the scope of the first introduction to stroboscope filters.